So we have done a number of optimizations on intermediate representation now. So what's left to do is now to generate code that is actually executable on our machine. So we need to translate our optimized intermediate representation to assembler or machine code. So this is the final part of our compiler, which is concerned with code generation. So what we have to do there is to map all these virtual registers we've been using in the intermediate representation, for example, when we did single static assignment. And so we need to assign all the variables to registers. Of course, in the common case, we have more variables than registers available. So if this is the case, we have to map variables to memory and load and store variables from and to memory as required. Essentially, what we have to do is we have to translate each assignment to an instruction. Depending on the instruction set architecture, some assignments may require more than one instruction. So, for example, some instruction set architectures don't have assignments for directly moving a large 32-bit constant into a register just because there's not enough encoding space in your instruction bits. So you have to split it up in 2 or more instructions. And finally, you have to emit all of your basic blocks. You have to put a label before each basic block so you can jump to it. You have to emit the assignments that are part of the basic blocks, and at the end of the basic block, as we've seen already, are branches. So you have to ensure that you branch to the correct following basic block when you generate code. So the next thing to do is you need to define an order how your basic blocks are laid out in memory. And this is very useful because this can help to remove superfluous branches, because branches mess around not only with your branch prediction in your processor, but obviously also with your pipeline. So perhaps you have to flush your pipeline when you do a branch. So every branch you execute in general reduces your performance. So if you can get rid of branches, this is the best thing you can do. And finally, you can do some optimizations that are specific to your instruction set architecture and your CPU. For example, you can reorder instructions if this would make some operations faster. This is something you cannot, in general, do on the intermediate representation layer, just because you don't know your CPU target at that point, because that's just part of your backend processing. So let's take a look at our code here. We have a bit of example source code on the left-hand side here. So just 2 assignments, a while loop, and inside of this while loop we have a simple if statement. So the first thing we do is we have translated this to an intermediate representation. So we start here, and then we define our first basic block. So the first 2 lines here are just assignments, so there's no branch involved, so they can be part of the first basic block. And then we have a while loop. As we've seen, we cannot directly express while loops in our intermediate representation, so we translate our while loop to a conditional branch. So if checking the condition, if x is not equal to y, well, then if this is no longer the case, we end our program. So we end up here. And as long as x is not equal to y, we execute our loop body here. So we have to translate our loop body into simple instructions. And this is just an if instruction. So if x is larger than y, this is again a conditional jump, so it ends the next basic block. We enter the left basic block here, and otherwise we enter the right basic block here. And then at this point in our code, our control flow joins back together. And as long as our loop condition is fulfilled, we just go up to the start of our loop and execute our loop body again. Now we can perform some loop optimizations here that already were performed on intermediate representation level. So for example, we can do some constant propagation and constant folding. So instead of y equals x plus 7, we have y equals 10. And so things can get quite a bit easier. So we can actually always execute the first loop iteration because we know it is always valid here, because obviously 3 is not equal to 10. So we jump inside the loop, and then we only take the branch back to the loop as long as this condition x is not equal to y is fulfilled. So our code generation starts with our optimized intermediate representation. We have some basic blocks defined. We know where our branches are jumping to. So now we have to translate this to some real code. So to do this, we start by numbering the basic blocks. So the first one up here is given the number 0. The single basic block with an if is given the number 1, and so on and so forth. So the numbers are arbitrary, just numbered then from top to bottom. And so the first thing we need to do is we need to do register allocation. Now here we only have two variables, so that's very simple. So let's assume our first variable x is just allocated to register 0, and our second variable y is allocated to register 1. Then we have to generate code for each basic block. So basic block 0 has two assignments here. So x equals 3 is translated in a move instruction that moves the constant 3 into our register we assigned for variable x, so r0, and y equals 10 is translated into the appropriate move instruction one line further down. Now, we have to generate additional code for this implicit branch here, because our basic block ends, so we know our basic block has to end with a branch, so we need to branch somewhere, and we always branch to basic block 1 in this case, so our final instruction for basic block 0 is a branch to basic block 1. Now we can look at the other basic blocks independent of that one. So basic block 1 is a more complex expression. So we have a comparison here that we have to execute, and then we have to branch depending on the result of our comparison here. So we do a comparison if less than. So if R1 is less than R0, so we're just switching the comparison around. We store the result in register 2, so we allocated a temporary register for a result here. If this is true, we jump into basic block 2 here, so to the left-hand side. Otherwise, we know it's false, so we jump to basic block 3 down here, which is that basic block. Now these basic blocks are very simple to translate, so this is just an assignment, so we subtract y from x and assign it to x again, and branch to basic block 4 at the end of basic block 2, and we do the similar thing for basic block 3. So what's left is to translate basic block 4. This is very similar to our translation of basic block 1, so we do a comparison, this time a comparison for equality. So we're again turning the condition around, and if the comparison for equality holds, so if they're equal, we jump out of our program, and if they're not equal, we jump back to basic block 1, which is the beginning of our loop. So all these code pieces for our basic blocks have been generated independent of each other, so they have not been assigned any memory addresses, so they're just text at the moment. And so what we have to do now is to define an order of these basic blocks in memory that actually makes some of these branches in our code unnecessary, so we can just leave them out. And that's what we're doing now. So first we start with our basic block 0, and this has, of course, our two assignments here. And then we know we always branch to basic block 1 here at the end of basic block 0. So if we put basic block 1 in memory directly after basic block 0, which is what we're doing here, we don't need this branch because our computer just continues to fall through from move to compare LT without being given this branch instruction. Now, here we have a conditional branch if true, so we obviously need to somehow put this into code in basic block 1 after our comparison, but we have an unconditional branch at the end of basic block 1, so this branch to basic block 3. So we could optimize our code now by shuffling the other basic blocks around. So if we put basic block 3 right behind basic block 1 in memory, we could just save this branch instruction and leave it out again. And that's what we're doing here. So we're subtracting, that's the assignment instruction, basic block 3 down here, and then we branch to basic block 4. We'll see in a bit why we can't leave out this branch. We could put basic block 4 right behind basic block 3 now. So that would be an option to leave out that branch, but we have decided instead to put basic block 2 in this place. So basic block 2 does the subtraction and would branch to basic block 4. And now we immediately put basic block 4 after basic block 2 in memory. So we have to decide if we want to leave this branch out at the end of basic block 2 or the other at the end of basic block 3. We need one of those to jump over the then or else case of our if. So in this case, we have decided to leave out the branch at the end of basic block 2. So we have basic block 2 at the end of after basic block 3. And then if basic block 2 has ended executing, it would automatically continue with the compare if equal. So that's the case on the right hand side here. Otherwise, it would just jump over at the end of basic block 3, so we wouldn't execute basic block 2 by accident. And then again, we have a branch if false, so we turned this condition around to jump back to the beginning of our block. And we did this to eliminate our final branch here to basic block 1, just because then we could, by turning around the condition we check for here, could directly fall through to end. So we reduced the number of instructions significantly. We eliminated quite a number of branches in our code here. So this makes our code execution quite a bit more efficient. So in summary, modern compilers consists of two major parts. We have our front end, which is machine independent, which does the analysis, which does checking of the correctness of our program, so syntactic and semantic correctness, and hopefully produces some meaningful error messages. And the output of our front end, if all goes well, is intermediate representation code, which is machine independent. And this intermediate representation code is then handed to our compiler backend, which does the synthesis, so it produces an optimized program that we're actually able to execute. So it optimizes the IR, it generates assembly, and it possibly also optimizes the assembler code we generated. And very often, this assembler code that modern compilers generate is of very high quality. So depending on your optimization target, it generates very fast code or very size efficient code or maybe very energy efficient code. And this is because the compiler knows more about the machine than the usual assembler programmer nowadays does, because computers have gotten more and more complex. So essentially, more or less, we can say that very often the quality of the generated assembly code that's output by a compiler, as a result of compiling your C code, for example, is higher than if you would hand code your assembly code. So essentially, there's very few reasons nowadays just to write something in assembly anymore.